Hello, my friends. Sorry I can't be with you today. I'll actually be gone most of this week. I will see you again Friday, possibly. But today I want to really start talking about wrapping up some of this lab stuff we've been doing with the floating water lab. So if you could open your lab notebooks up to the floating water lab, that would be fantastic. All right, so if you need more time getting your stuff out, hit pause, make sure everything gets out, but we're moving forward. So we did the brass ball demonstration the other day where we heated up the brass ball. It would fit through the hoop. We heated it. It didn't fit through the hoop. And we said, well, things expand when they're heated. And then the question is, well, why do they expand when they're heated? So hopefully in this point right here, you're able to explain this in a few key terms. First of all, hot. Well, this is not going to write well. I'm not going to write then. We'll have to live with just talking. So hot means that the particles are moving faster. And when they move faster, they're going to crash into each other and hit each other harder. And when that happens, they push each other farther apart. And that's why heating a solid, like a brass ball, tends to make it expand. Because they move faster, hit harder, and push each other farther away. Now this question down here is, well, why does dye mixing into water, why does it stay mixed in? Why doesn't it fall to the bottom or float to the top? Because it's likely that it's either heavier than water or lighter than water. And that's true. It really is either heavier or lighter than water. And the reason it stays dissolved in and mixed in is because the water is moving around. And when those water particles are moving around all over the place, bashing into each other, they also bash into the dye. First of all, knocking into smaller pieces. That's why it dissolves. It breaks apart because it's getting bashed into by water. And also, those moving water molecules then bash those tiny dye particles all over the place and just plink it around everywhere. And that's what keeps it mixed in. It's because water is constantly moving, doing the mixing for you. Now, as we heat water, just like in the brass, they move faster. So they're going to be able to break off chunks faster, so things dissolve faster, and they're going to keep things spread out, and they're going to make that spreading out happen faster. So those are the key ideas that we should have by now. Now here we stacked the hot water on top of the cold water, and we pulled the divider away. It did not mix. The hot water stayed on top. And we know that things that are lighter, less dense than water, float. So somehow that hot water must be less dense than water, than the cold water, I should say. And we explain that on the terms of the hot water, the particles are moving faster, hitting each other harder, pushing each other slightly farther away. So they end up being less dense because they're slightly farther away than the cold water is. If we let this demonstration sit for a while, the temperatures would be equal, and then the molecules would just slowly start mixing as they bashed around into each other. And over several weeks time period, it would all be purple, but it would take a really long time to happen. Now this one down here, we flipped it over and we said, hey, what would happen if we put the hot water on bottom, cold water on top? And sure enough, that cold water where the particles are closer together because they're not moving as fast, they're pulling in closer together, sinks right to the bottom of the hot water and they mix relatively quickly in just a minute or two. You'll get significant mixing. Okay, so down here you should be saying number 12, check out number 12. So why is the hot water? So there should be hot right here. I'm gonna try and write again, see what it looks like. Kinda, it's really hard to write on the PDF, I guess. So why is the hot water less dense? And that again, moving faster, hitting each other harder, pushing each other farther apart. Fantastic. We have a mechanism for why things become less dense or expand when they heat. Now in this one, you can see the picture to the I don't know, left or right, whichever way it is, that way. And that picture is going to show you a common result of the liquid challenge, where we try to stack up water on top of a penny. And that's not exactly this one, but it is this one down here, the penny drop challenge. And what we find is that water can have a big old glob on it, and acetone barely has any before breaking off and falling off the sides. And what the explanation is for this means that water must be, let me see if I can draw it real quick. This is going to be tough to do. So there's my penny. It's a little lopsided, but then my water looks like this. Check this out. So whoops, I'm moving it now. So my water looks something like this. Well, that's frustrating. So my glob of water looks like this. It's like, oh, I've got a circle. This is not fun at all. Okay, so there's that. And now my water is going to look like a glob, like, and then my penny. Let's see if I can draw a penny with a rectangle tool. Nope, it's not going to like this. Here's my penny. I'll draw it in red, and I'll try to move it right to there. Oh, beautiful. And then acetone's way down here. It's like a terrible one. And I'm going to just take this penny and I'm going to paste it and drag it right to here. And then I'm going to draw my acetone just like so and move it into place. It's like, whoo, like this. It's not even very, it's like that's even exaggerated. Like it's not that high even. It should be like here-ish. So we can see that the water really gloms together well, and that means that those particles of water must be super sticky. They're actually sticking to one another, and the acetone is not very good at being sticky. So it doesn't stick well together. I don't know how to make that box go away. Oh well. So that's a result of that one. It's a really cool idea that we can actually see how sticky the particles are by how big of a glom they form. And let me show you something else. Check out this one. This is that steel ball we were using earlier. And this guy, I mean, it must be super sticky because it doesn't slump at all. It doesn't flow out into a pool. It stays all together. These chunks of metal, these little particles in there must be really held together strongly. They must be super sticky to each other. All right, and then let's go back a little bit and take a look at, so we know that water must be super sticky. That's why I can create this big blom. And if we come back up here to the liquid challenge, when we drop 2 drops of liquid, can we now understand why the acetone made a really, like, not very thick blob, but really spread out? Whereas the water made a less spread out blob, but thicker, even though they're roughly the same amount of liquid. And of course, that has to do with how sticky the particles are. So the acetone doesn't stick well together, so it spreads out into a thin layer. Whereas the water sticks really well, so it bunches up into a glob. And from there, you can figure out the ethanol and methanol. Methanol should be here, like next to sticky, or next to least sticky, and then ethanol is a little bit more sticky, but not quite to water. Now, if we understand evaporation as this process where the particles break off from each other and fly around the room, then why would acetone evaporate the fastest then? Take 30 seconds right now. Talk to the people at your table. Try and answer that question. Answer the question, why would acetone evaporate the fastest based on what we know about the stickiness of its particles? Go ahead and go. You can hit pause. We'll come back to this. All right, awesome. So now we're at the point where we're trying to answer this question. Hopefully you guys came to the conclusion that, hey, if your particles stick together really well, it's going to be hard for particles to break off. Therefore, you're going to evaporate slowly. So again, if we take a look back at this, we know the particles stick together really well because it stays in a ball like this. It doesn't slump down to a liquid or into a flat spot on the table. So we might expect this not to evaporate very quickly. And sure enough, if we leave this here and go look at it tomorrow, it's going to look really the same. It's going to be very little evaporation happening. Awesome, good news. So the more sticky you are, the slower your evaporation rate, the harder it is for particles to break off. Nice. We have this awesome model now that's able to predict lots of cool things. And then number 18 here, this is a good one to really think about. It's like, why don't all the molecules evaporate instantly? Well, it's because of that stickiness thing, right? So they stick together some. It's only the ones who are moving fast enough that can break away from that stickiness, but not all of them can. They're sticky. All right, let's jump down here. Now this demonstration we'll do when we get back. So let's leave this leaky demonstration thing off for now. And then the matter in the bag will also do the day I get back when I see you guys again. I believe that's going to be Monday. We'll knock out those 2 things. Right now, though, what I want you to do is you have a worksheet to work on. It is called understanding matter. And you're going to work on that as groups. You're going to help each other with it. Really get to the point where you understand the questions and what they're asking and what the answers are. And then afterwards, you're going to be taking a checkpoint quiz called Mixing Liquids and Blowing Up Balloons. Just kind of see where you are in all this material. All right. Best of luck to you. Have a great day. And remember to behave well. Have a nice day, my friends. Bye-bye.